Alright, this is a short video tutorial all about momentum. I'll just kind of read the top at the beginning there, and we're going to delve into this. Now, the thing you can see at the top, it's super useful concept in physics. So later on in the course, when we start to learn about colliding objects, so car crashes, marbles colliding, anything really, all the way to planetary systems and galaxies and everything. During the collision of objects, we're going to learn about how momentum is transferred from one object to another, what happens to kinetic energy, what happens to momentum during those collisions, and be able to solve some really complex problems that are very useful in the real world. Now, you've probably heard of the word momentum. You'll hear it somehow related to inertia at some point. Although inertia doesn't really have a numerical value associated with it, momentum is different. Momentum is calculable, and you are able to get a value from it, and that value has meaning. Inertia is an extremely important concept, and is still related to momentum as a conceptual understanding of it. So with momentum in your tool belt and understanding inertia, you'll be able to really sort of grasp what's happening in the real world. Secondly, a really important fact to know about momentum is that Newton's second law was actually written in terms of momentum. And so Newton's second law, which is the net force acting on an object, is equal to the mass of the object multiplied by the acceleration of the object, or F equals ma for short, or F net equals ma. And so Newton actually didn't derive it like that originally. He wrote it as the change in momentum over time. And we're going to learn more about that later. You do need to understand a little bit of calculus to understand that the rate of change of momentum with time is really a derivative. And understanding that derivative, or the rate of change of momentum with time, and since momentum has a velocity component to it, what you're really looking at is the change in velocity over time. And the change in velocity over time is clearly the acceleration of an object. So, and then you multiply it by the mass, and you get m times a. And we're going to do a formal lesson on that coming up soon. So, I wrote here, in fact, you'll learn the momentum and impulse are more general forms of Newton's second law. And in fact, this is how Newton originally presented them. Okay. Later on, we're going to learn the importance of the conservation of momentum, which is an incredibly important concept in both linear and angular as well. We're going to focus mostly on linear and not the angular, but we can talk about that as well. All right, so what is momentum? Well, Newton was thinking about problems, and he quickly realized when he devised Newton's second law, his second law, which I don't think it was called that back then, he discovered that you could do something with the mass of an object and the speed of an object and calculate a value from it. And so he came up with this idea that momentum, P, is the mass of an object multiplied by the velocity of the object. Notice the vector signs, meaning that whichever direction the velocity is pointing is the direction that the momentum is pointing as well. And so simply it was a mass times a velocity component. And what's interesting about this is it was really talking about how much force an object could apply to something if it was moving. So if you imagine a bowling ball, let's say you're laying on the ground and a bowling ball is rolling towards your face at a very good speed, you're going to be upset because it has a lot of mass multiplied by a velocity, which gives it a fairly high momentum, or that force of impact is going to be high. So this momentum is somehow also related to the force of an object, hence where we're going to get into Newton's second law. Whereas, think about a little marble coming at you at the same speed as that bowling ball. If the velocities of those two objects are the same, but the mass is very small, you're not going to be upset about that little tiny marble hitting you in the face, right? It's just not, it doesn't carry the same sort of impact. Be the same thing with a Nerf gun. So the Nerf bullets, although they travel quite fast, they have very low mass because they're made of that foam material. And because they have so little mass, even though they're traveling really fast, the force of impact or the momentum that they're carrying is quite small, right? And now something else to think about is, if you think about light travels extremely fast, but it has no mass. And so we don't worry so much about getting hit by light particles. We're going to learn later that, zero mass times the speed of light is zero, so it shouldn't carry momentum. But Einstein, E equals mc squared, is going to come into that later, and we're going to see that there might actually be some momentum that is carried by photons of light. So this formalization of Newton's second law, or in this case, just the momentum part of it, P equals m times v. So it's a multiplication of these two. This is a scalar value multiplied by a vector value. What are the units? Well, the units of mass are kilograms, and the units of velocity are meters per second. So it's kilogram meters per second. That is the units of momentum. Okay. Difference between inertia and momentum. So mass is a fundamental measure of inertia. It measures the resistance of a body to changes in motion. I've gone on about that so many times. Thus, inertia is the resistance to change in motion, whereas momentum is mass in motion. So that is the big difference. One way to think about momentum is mass in motion, whereas when you're thinking about inertia is the resistance to change in motion, whereas momentum is mass in motion. So you might want to highlight that, put a little box around it, and realize that that is what momentum is, right? And so it's defined as mass times velocity. Okay, so where can we go from here? Well, we're in day one of this, so we're going to go through this pretty quick. Let's say you have a truck right here, okay, and it has a mass of 8,000 kilograms. All right, and it's traveling at just 10 meters per second. If you multiply by 3.6, you've got 36 kilometers an hour. Calculate the momentum of the truck. So we're going to say P equals m times v. The direction is positive to the right, so we can drop the vector signs in this case. We put in our values. 8,000 times that carries a momentum of 80,000 kilogram meters per second. Okay, pretty straightforward. Now consider there's a turtle has a mass of 5 kilograms. How fast would it have to move so that its momentum would be the same as the previous question? Okay, so this is the momentum of the turtle. We want it to be, I'm going to rearrange it first. It's P over M. That's obvious. And the momentum is going to be 80,000 kilogram meters per second. I'll put the units for the note here. Divided by the mass of 5 kilograms is going to leave us with meters per second. So this thing would have to be 16,000 meters per second, or divided by 3.6, about 4,444 kilometers per hour. Yikes. That would have to move pretty fast to carry the same momentum as that truck. Not likely. Obvious. Okay. What can we do from here? Well, what we're going to see is that I've done that calculation incorrectly. That's the first thing you're going to see. And remember, if you're going from meters per second to kilometers per hour, you multiply. So it's actually 57,600 kilometers per hour, which is just crazy fast. Okay, so let's take a look at some other problems and see what we can do with it, and then we'll get to the problems you're going to work on. All right, so the first one is some practice problems. Using the momentum equation, solve the following problems. Calculate the momentum of a 200-gram marble traveling at 20 meters per second. That's actually very fast. 20 meters per second is twice the speed that the fastest person in the world can run. It's about 72 kilometers an hour. It's moving quite quick. So to find the momentum, And again, it is a vector, 0.2 kilograms, so you divide by 1,000. It's 4 kilogram meters per second. Okay, that's it. That's all you need to do. Box your answer. All right, so next one. Calculate how much kinetic energy an object that has a mass of 30 kilograms has. Oh, that's bad grammar. It has a momentum of 200 kilogram meters per second. So we know the momentum is 200 kilogram meters per second. The mass of it is 30 kilograms. And it has that momentum, that mass, and it says calculate the kinetic energy. So we know that kinetic energy is mv squared over 2. We did that derivation last year from the work energy. We found that work is force times distance. Force is mass times acceleration. So that's the MAD equation, ma delta d. We know that acceleration is v2 minus v1 over t. And then you multiply it all out, do all those stuff, and we find out that the work done is mv2 squared over 2 minus mv1 squared over 2. And if you started from rest, mv1 is 0, and therefore the kinetic energy is just simply mv squared over 2. If you didn't follow that, it's what we did last year from the work energy, from the work unit. So we have this situation. We're trying to find out EK, but we don't know the speed. So what we do is we realize that P equals M times V, where we know the momentum, we know the mass. Here we know that, and we know that. So we can rearrange this for V, and that's what you get. Now, I'm just going to do the substitutions here just for fun. And that's going to give M P squared over 2m squared. One of those divides out, you get p squared over 2m. Now the units at the top is going to be kilograms squared over meters squared per second squared. And when you divide by kilograms, you're going to be left with 1 kilogram on the top. So you're going to get kilograms meters squared over second squared, which is the units of a joule, or energy of 1 joule is a kilogram meter squared per second squared. So therefore EK, I'll just show a little substitution there. This is a neat little formula to keep in the back of your mind when you're solving problems. But again, you could just solve for the speed and substitute the speed in. It would do the same thing. Now, just go 200 squared divided by 2 divided by, 30? Is 667 joules of energy. Now remember, 1 joule, I'll put that up here, like 1 joule is a kilogram meter squared per second squared. Okay? And that's, that's basically where we got that unit from, because the top is kilograms squared, meters per second squared, meters squared over second squared, and then divided by the kilograms. Okay? Let's try another one. A monkey is swinging from a tree. At the bottom of the swing, it has a total momentum of 30 kilogram meters per second and is moving at that. Calculate the mass of the monkey. Now I'm going to solve that one. You're basically trying to solve for m. So you can just rearrange first and do your substitutions. In the one below here, a truck has a kinetic energy, so we know the EK. And we know the momentum, and it says calculate speed. Okay, so you can write those things out. If this is the case, you can actually, we know this is m times v, we know this is mv squared over 2, and then you can work backwards. Actually, you probably can't do this question if you're looking at it, because you're going to realize that you're going to have P equals M times V. And here you're going to have EK equals MV squared over 2. And if you do all your little fancy substitutions by substituting in, actually you could do this because I think the first thing you're going to need to find is if you do the substitution like we did before, you can figure out the mass, and then once you have the mass you can plug it back in to get the speed. So that's a neat little problem actually. So I'm going to leave that for you to do. I would urge you to look up here and look at the substitution we did here and then rearrange that formula, and you can find the mass, and then once you get the mass you can figure out what the speed is. Okay, number 5. And so this is just to get you the idea that, you know, what happens to the dynamics cart is moving forward, it has a certain amount of momentum. What is the momentum if the mass of the cart is doubled? So we know that the governing equation is P equals M times V. Okay? It's linear in both terms. And since it's linear in both terms, we know that if you double the mass, you will double the momentum if the speed stays the same. So this is simply 50 kilogram meters per second. What happens if the speed of the cart is tripled? Well, the speed of the cart is tripled, 75 kilogram meters per second, because if this triples, the momentum triples. If that doubles, that triples, or that doubles. The speed is quadrupled, so now there's 4 times the speed, and the mass is 1/3. So, see if you can figure out what a quadrupling of the speed and a 1/3 of the mass would be for that question there. Okay, let's see what you get for that answer. Okay. The work you're going to do is the first part is your warm-up, and you're just going to quickly go through these. It's not too hard. So it says write the equation for momentum and kinetic energy and write the units for both. So we know that's the equation, and the units are kilogram meters per second. And down here, this is scalar. There's no vector signs on this because energy is scalar. So the units for kinetic energy, I wrote it, I guess you could have, I think it wanted both equations at the top and then the units below, but I did it this way, that's fine. Okay, and the units are, that's a kilogram, and speed squared is meter squared over second squared, and we call that a joule. Okay, answer the questions that are on the sheet here, and on the back you'll see as well Rocket Mouse, and you're going to answer some questions about Rocket Mouse as well. Alright, so give those a shot. I'll post the solutions to these after this video is done. Alright,